Okay, so what we're going to do is we're going to record this session, and it's going to take about 30 minutes to an hour for it to actually be available as a video, but it should be done by the time we're out of class today. So again, on Monday when we met, we discussed node voltage analysis, and today we're going to do mesh current analysis. We started doing mesh current just a little bit, and we just got to the algebra part, but I'm going to go ahead and do the lecture here. So for this lecture, what do we have? 11 slides. It's not that long. It says here the dual of the node voltage method. It's just, I guess, a little joke. Mesh current or node voltage. When you are confronted with a circuit, you'll get to decide which method is easier for you to actually solve for the unknowns. So in mesh current analysis, you're going to use KVL equations around meshes, and then you're going to solve for currents directly. So in mesh current, you're looking for current directly, but you're using Kirchhoff's voltage laws. Remember, as we're in node voltage, we were looking for voltages, but we were using Kirchhoff's current law. So, and then we're going to talk about some special cases for dependent sources and for current sources that are inside a mesh. We haven't actually done anything with dependent sources, either dependent voltage or dependent current sources up until now. But they're not much harder than any other element that you'll find in a circuit. Okay. And so the basic mesh current method, again, this is the recipe. Again, for your exam, you're allowed to, I'm okay with you bringing in things like this on a cheat sheet. So the steps to help you know what to do next on a problem. This is not by any means a problem for me. So step one would be to identify the meshes, and we discussed what meshes are, but we'll do that again. Label each with a mesh current, so basically just number them or identify them. Write a KVL equation around each mesh. Put equations in standard form and solve, and check your solutions by balancing power. Again, all power has to balance. And then calculate quantities of interest to make sure that we solve what it is we were initially looking for. And then last week, I think everyone got the concept of node voltage. It was just the algebra that we had to review a little bit, and that's not a problem. So after I'm done with this recording and we get back to class, I have no problem. We'll go over a problem or two, and we'll actually cover the algebra in more detail than is shown here. Okay. So again, it says here, how many meshes does this circuit contain? And I don't actually have a mouse with me right now. And I don't think you can see my mouse pointer, but let me go ahead and draw on here. And remember we said the mesh has to be like the smallest loop possible, right? Where you can't break it down any further. And so if you count this as a loop, I know that doesn't look like awesome. You got to tell me what you did so we can put on like a frequently asked questions later for people who have problems on their phone. Okay, back to the lecture. So this is another loop. And again, I'm sorry I don't have a good mouse to write with. And this is another loop. Now you can see that you can't break these loops any further. And so that's a good indicator that you have a good mesh. Right? And so to answer this question, how many meshes does this circuit contain? 1, 2, 3. Now also know that you could also write an equation around the outside, right? Through this voltage source, this 30 ohm resistor, this 8 ohm resistor, all the way back to the source. That's good, but again, that contains a bunch of mini loops. So this one right here, put it in a different color. Should have written it in red. And I just put like a little X here. We don't want this one, right? That's not good. And again, you can see we could do loops through many other crazy loops around the circuit, through the 80 volt source, the 5 ohm resistor, through the 90 ohm resistor, 8 ohm resistor, all the way back to the source. But then we'd have that 26 ohm resistor breaking that in half, and so that would also be a bad loop. Not a bad loop, but it would be too many variables in there. Okay. And so again, this is the way the author does it. And by convention, and I'm going to let you know to do the same thing, just go clockwise. You can actually get the exact same numbers and the same values if you wrote those currents going in the opposite direction. But you kind of want them all going in one direction, in this case clockwise. If you decided you just like going counterclockwise, it gives you the exact same outcome. Your signs will be different, but everything will balance out. But we're gonna, for convention, we're gonna draw these loops like this I1 going from the 80 volt to the 5 ohm to the 26 ohm. We're gonna just say clockwise for our convention here. So the problem is find the power associated with the voltage source and the 8 ohm resistor using the mesh current method. And so we're looking specifically, like I said before, at the very before. So we're looking for the voltage power. So we're looking for power around this 8 ohm resistor. And so in order to do that, I need to find the current going through the 8 ohm resistor. And we're going to use the formula at the very end to solve for power. P is equal to I squared R. And for this, I'll do I squared R. And I know it's hard for you guys to probably see that up on the screen. All right, and that's an equation for power loss because the resistor consumes power. Okay, so let's go ahead. I'm going to walk you through each loop, and we're going to start off with loop I1. All right. So starting off with, and I know you can't see the mouse. I'm just going to put a little dot every time I talk about something. Like, we'll do orange because this is an orange. So if we start off identifying everything in this loop I1, the first thing you kind of want to do is set up a sign convention. So if we're looking at this loop just by itself and pretending none of the rest of the circuit was there, we could say that we have current going from the 80 volts source through this 5 ohm, through the 26 ohm, back to the source. And we set up a convention, and let me try to do it this way, right? We can say that it goes from plus, oh no, I'm erasing everything, because it's, oh good. We do that there from plus to minus, and then here we do plus, oops, to minus. And that's how we set up our values. This sets up the sign notation. So we're looking at current 1, mesh 1, right here. We'll start off with the first component, and we start at the bottom left corner here, and we go up. We're going to hit the negative sign of that source of that voltage, and so we'll say it's minus 80 volts, which we have right here. And now this one, they've already done the distributive property for you, but we'll work it out. I'm going to have to go a little detail over the 5 ohm resistor. So what we have here is 5 ohms times I1, since I1 is going in this direction. Now we also have, in this second term, which I'm talking about right here, we have 5 ohms minus I2. And the way we get that, again, if you look at the I2 loop, right, it's going, again, in the clockwise direction. Notice that the current for I2 going to that same 5 ohm resistor, it's going plus to minus, but from right to left. And just to show you what I mean by that, I'm going to put minus right here, and plus right there. And so if we're looking at I2, I2 is going across that 5 ohm resistor, right here, but it's going in this direction. Dang, I really wish I had a better. As for I1 is going in this direction. So we have these currents, the way we've drawn them, going in opposite directions. So we're going to have, if we're looking at the mesh current through I1, it's going to be I1 minus the current going opposing it, which is I2 in this case. And so it's 5 ohms times I1 minus I2. And we'll do an example in class before you get to your lab, because we're going to do this for lab coming up next. Now we're going to do the same thing with the 26 ohm. So now we're here with the 26 ohm. Now again, in this mesh we have the I3 current. And again, by convention we said I3 is going in clockwise direction. But if we saw where I1 is going plus to minus from the top down, I3 is going plus to minus from the bottom up. And let me go ahead and write that as well. If you look at it like this, that's plus. Oh, and then right there, and that's minus. So if we're looking at the current, the resultant current going across this 26 ohm resistor, we have I1 going in one direction, and we have I3 going in the opposite direction. So the resultant current there is going to be the subtraction, the difference between the two. So we'll have 26 ohms, and now again, I'm on this term right here. Oops. I'm on, so you guys can see what the 26 ohms times I1 minus I3. And this all has to balance out to 0 because KVL says all the voltages in a loop have to sum to 0. And that's it. We're done with the first equation. Now again, remember we're doing this all with reference to I1. So that's why I1 is always positive in this direction, because we're looking at current going from plus to minus across the 5 ohms, and then plus to minus going across the 26 ohms. And what's opposing that in the 5 ohm is that I2 current going in the opposite direction. And what's opposing I1 and the 26 ohm resistor is I3 going in the opposite direction. So I1 will be positive in this first equation. Oh, sorry, Tristan, I didn't see that you had raised your hand. Okay. Okay, I just saw that it said you lowered your hand. Did you have a question? I just put it on the chat, or 26 ohms being added. So let me clarify or restate that. So again, if we're looking at this, because it is going in the opposite direction. So when we're at this 26, yeah, so let me clarify with the 26. So when we're looking at the 26 ohm resistor, which is right there in that center branch, and we're looking at the 26 ohm resistor with reference to the I1 loop, it'll be 26 times I1, and that'll give me that voltage drop there, minus I3 going in the opposite direction times 26. So we're actually subtracting the two voltage drops. Hopefully that helped. We're going to do I2 and I3, and then by repetition, hopefully this will make a little more sense. And let me erase, because this is being recorded, so I think everything is it's going to be there. So let's go ahead and do I2. And I2 is this top mesh up here. Right here. Okay. And so we have, and we'll start at the very, very top. We have the voltage drop at the 30 ohms. And again, by convention, let's go ahead and set up our notation, our sign notation. And since we're going clockwise, we're going to say, it's from plus to minus here. And then right here, right, that's minus, plus, I'm going to do the same thing over here. Now, if you look at it like this again, and we're going in the clockwise direction, we say current is going from the left to the right across that 30 ohm resistor. And as we come back to the 90 ohm resistor, it's going from right to left because that's the direction of the current. And as we go through the 5 ohm resistor, again, it's going from right to left. So the voltage drops are going to be in this sign notation. And then if we're looking at, and I'll go ahead and do the sign notations again for I1 and I3. In this case, it stays the same. This doesn't change. You can see they're going in opposite directions. But everything's going to be in reference to I2. So now here we're at the I2, and I'll do this in a slightly different color, green, so it doesn't kind of blend in. So right here we're now at the I2 mesh. And so the first thing we're going to do is we got the 30 ohm resistor up here on top, and it has the only current going through it, which is I2, and it's from plus to minus. So it's going to be a positive 30 ohms times I2, which is this first term right here. Those are kind of easy because they're by themselves and they're not part of another mesh. But here we're going to go to the 90 ohm resistor, which is right here. And as you can see, the 90 ohm resistor is connected to two meshes, I2 and I3. So we're going to have to go ahead and do the difference in current between those two meshes. So 90 ohms times I2, and again, since we're doing the I2 mesh, the I2 is going to be the positive, and I3 is going to be going in the opposite direction of I2, and so it's going to be 90 times I2 minus I3. And then we do the same thing for the 5 ohm resistor, which is right here. Right? And again, the voltage drop is going from right to left. And so we have a positive 5 ohms, obviously. Ohms is neither negative, I mean, it's always positive, times I2, and that'll give me the voltage drop going in the right to left direction. But we also have the current I1 going in the opposite direction down here. And so we're going to have to subtract the current I1 going in the opposite direction across that 5 ohms. And we set that all equal to 0, and that gives us our second equation. Right. Now we kind of already know this from algebra that we have 3 different currents here, I1, I2, I3, and so we're going to need a third equation. And so let's go ahead and do I3. Now, I wish I could just erase part of this, but I'm going to just pick a different color because I don't want to redo all the sign conventions. Let's go ahead and do red. Should be easy to see. Okay. So now we are on I3. Right here. And let's make sure all our sign conventions are set up. So we do have the sign convention here for current going through the 5 ohm, through the 90 ohm, but we don't have it going for the 8 and the 26. So let me go ahead and redo those. So I3 is going clockwise. So that means we are going from plus to minus here. And across this 26 ohm, we know that I3 is going from minus up on top and plus in the bottom. But I1 is going across that 26 ohm resistor in the opposite direction. So remember, this is going from, let me get it a little closer, plus to minus. Okay. And so we set up our sign convention for the entire circuit. And this is probably the best thing to do. It's not on that list of your recipe, but set up the entire sign convention because that doesn't change. And this will actually help you write out your equation. So let's go ahead and write out the equation for I3 mesh, which is the lower right-hand corner here. And we start off with the 8 ohms because it doesn't have anything else that it's connected to. And so we can simply say it's the voltage drop, which is a plus 8 times I3, which we have this term right here. Oops. All right. And then we're going to the next resistor, which is the 26 ohm. Now again, the 26 ohm has 2 different currents going across it. The one mesh through I3, which is going plus to minus, and I1, which is going in the opposite direction. So this would be 26 times I3 minus I1. And then we continue to the 90 ohm. I really need to fix my drawing board so I can actually draw this better. And so the last one would be the 90 ohm. And again, the 90 ohm has I3 going in plus to minus direction. So again, I3 was always going to be positive. But we're also going to have to subtract the current that's going in the opposite direction for the 90 ohm which is I2 on top. So I2 is going in this direction. And so the last term would be 90 times I3 minus I2 equal to 0. So this very last part, I'm not going to go over here in the recording, because I'm only wanting to discuss the concept of mesh current. The rest of this is algebra. Again, you can simplify these terms, combine like terms. On Monday, I think we did either substitution was one of the methods that we used, or we did elimination. And those are two valid algebraic techniques that you use to actually solve for the individual terms. And by doing this, they get I1 equal to 5 amps, I2 is equal to 2 amps, and I3 is equal to 2.5 amps. But that isn't what we're being tasked with solving. It says find the power associated with the voltage source and the 8 ohm resistor. So if I want to find the power for the voltage source, we're going to look for power being generated, and power generated, we know, is equal to I times V. I'm going to do this in caps so that you can see it better. And if we're looking for power loss, all right, we're looking for, in this case, since we already have current, we can do again, I'm going to do it in caps. I squared times R. Okay. And so now we can look for those specifics that it's asking for after we solve for all the currents. And again, the 8 ohm resistor is with 2.5 amps times the 8 ohms, which is 50. That's one of the things that we're asking for, which is right here. Oops. And then we're also looking for the power being generated by the 80 volt source. And again, that's current times resistance, which gives us 400. Now it also says to go ahead and balance out the circuit. So if you do the individual powers across each element, they should all add up to 400 watts. So that we got negative 400 watts here that we can spend, and it's all being spent on these resistors. And these, if you add up these numbers, they have to add up to 400. Okay. Now this one I'm going to have to check with the author because I think there may be a mistake here. So it says if you were asked to use the node voltage. Okay. So I don't know why they're asking for node voltage on this particular lesson, because this lesson is about mesh current. It says if you were asked to use a node voltage method, how many equations would you write and solve? And again, it's saying you have 2 KCLs with 0 restraints. Unlike if you're doing this same circuit with mesh current, you'd have to write 3 equations because you're looking for I1, I2, and I3. So if you were to get this circuit and you knew it very well from node voltage and mesh current, one of them you're going to have to do an extra equation. And so you may not want to use mesh current for this particular circuit. You may want to use node voltage because you're only having to do 2 KCLs. You'll still have the third node down here, but remember this is always going to be a reference. There we go. Okay, now we're going to do one special case here, which is dependent sources. And once I'm done here, I'm going to let you get to your lab. So mesh current method, special cases. So this is when we have dependent sources. So far we've only been talking about independent sources where nothing's affecting them. But this actually depends on another element in the circuit. And current sources on the perimeter of a mesh. So we're going to have a current source on the perimeter and current sources shared between 2 meshes. Okay. And again, the recipe for this is similar to the rest. Identify the meshes, label each with a mesh current, write a KVO equation around each mesh, and then are there any dependent sources? You ask yourself at this time. If so, write a constraint equation defining the controlling quantity for the dependent source. And we'll see what that looks like in the next slide. And then put equations in standard form and solve. Check your solutions by balancing power, and then calculate quantities of interest. Okay. And again, now you can see that we have our independent source, a voltage source right here. And we have our dependent voltage source right here. And I'm going to ask you all a question. I mean, you can type it out. What kind of dependent voltage source is this to the right? Is it current controlled or voltage controlled? Because once we get to dependent voltages and dependent sources, they can either be dependent, or they can either be current controlled or voltage controlled. And by looking at this, okay, so we know that the value of this voltage source is equal to 5 times I phi, and I phi is this current all the way to the left, right there. And so this means that this voltage source is classified as a dependent current controlled voltage source. Or you can say it the other way, current controlled dependent voltage source. Let's change the descriptors in any way you want, as long as they're all in there. And again, so what this is saying is the voltage drop across this source right here, there you go, is going to be 5 times whatever the current is going through, 5 times the value of whatever the current is going through the voltage source, the independent voltage source. So if I had, for example, 2 amps running across that 25 volts, oh, let's see, so let's go ahead and do this real quick. So let's say I have this 2.5 amps going across, I1's up on top. Dang it. Okay, let's do the actual values. I3 is down here at the bottom, and it's equal to I phi, and so we have 4 amps going across that voltage source. So I phi is 4 amps. So this is telling me that the voltage drop across this dependent voltage source is 5 times 4, which should be 20. Right. Okay, so I'm not going to do all the sign conventions like we did before, but I'm just going to go ahead and run real quickly to the I1, I2, and I3 meshes. Now, again, the author wrote this for us, and so he put I1 up on top, I2 to the bottom right, and I3 to the left. Just make sure this is one of the problems, or one of the areas where people have problems, and you see where I just kind of assumed that I1 was at the bottom, and it isn't. So make sure that you're sort of being an accountant and keeping track of what is where. And always write your meshes the same way. If you're starting from the bottom left and working your way all the way around, just kind of do that way, have your own method. That way you have your own accounting practice that will help you keep track of all these little things. Because if you start mixing it up, you're gonna make some mathematical errors. So I1 is, and we're gonna start from, which is here at the top, it's 2 ohms times the I1 mesh, and then we're going across the 8 ohm resistor. And again, that has 2 opposing currents, I1 and I2. So it's 8 ohms times I1 minus I2. And then we're going to this 6 ohm resistor. And we have 2 opposing currents, I1 and I3 in this case. So it's 6 ohms times I1 minus I3. And to balance it out, it has to equal 0. And that was just the I1 mesh up on top. I2 mesh, which is down here in the lower right corner. We're going to start off with the one element that's not dependent on any other branch. In this case, it is. It's a dependent source, but it's by itself. So we can just write it out by itself. It's 5 times I phi, and which we did right down here. Right. And then we're going to go through the current 8 ohms in the middle branch, which is, try to draw right there. I'm right here right now. And so that is 8 ohms times I2 minus I3, because I2 and I3 are going in opposing directions across that 8 ohm resistance, plus, and then again, I'm back up here in the tops, 8 ohms times, in this case, we have I2, and the opposing current is I1 up on top, so it's 8 ohms times I2 minus I1, and that is, again, balanced out equal to 0. And finally, the last mesh is I3, which is down here in the bottom left corner. And we have, again, starting off with our voltage source, it's minus 25 volts. And then we're moving to the 6 ohm resistor right here. It'll be 6 ohms times I3 minus I1, since they're opposing in that area. And then the final element in this mesh is the 8 ohms, right there. And the 8 ohms is I3, and the opposing current in that element is I2, so it's I3 minus I2. And then we set that all equal to 0. Now we do have one constraint. We know that I phi is equal to I3 in this case, because I phi is going across this voltage source, and it's nothing else in parallel with that voltage source, so that we know, or whatever that element is, if it's all by itself, we know that that current is equal to that mesh current. So I3 and I phi are actually the same here, and so now we can do a simple substitution here. And again, we'll do the algebra in class as review. Most of you have algebra, or actually some of you have more than algebra. But if you do, again, a system of equations, and again, if you're having a problem with this part, I would suggest that you grab an algebra textbook from the library or go to the math lab and ask them to help you out with systems of equations. Ask the math people to help you with this, I guess, this part down here. They're not going to understand the circuit part, but they will understand the mathematics part, and they can help you solve these 3 equations multiple ways. And there may be a better way that that'll help you. You can also do matrices, but from Monday's lecture, I saw that some of you frowned at matrices, but that's okay. Okay. And so when we solve for all the individual powers, this is what we get in the table. You know, the power generated is by the source, by the independent source, and everything else is being consumed. So again, all of these, if you add these powers, should equal to 100. And the very last question, I don't think you can read this up here, but I'll read it for you. If I phi is equal to 4 amps, and I1 is equal to 2.5 amps, and I2 is equal to 2 amps, what is the current in the middle 8 ohm resistor from plus to minus? So we're looking for, basically I think it's asking you for V naught. What is V naught here? So we're given I1, I2, and remember that I phi is equal to I3. And I'll go ahead and set this up for you. So if we're looking at the voltage drop across the 8 ohm resistor, put 8 ohm, that's going to equal to the current going through that 8 ohm resistor, so it'll be 8 times, and since we're going from plus to minus, it's telling us we're in mesh 3, which is the lower left, which would be, and I can't use subscripts here, but it would be I sub phi minus I2. I know that's not easy to read, but that would give you the voltage drop across I2. And if you have any questions on that, please send me a message, or even right now, send me a message, and then this will be it, and we'll get back to class. Everyone okay with this? Okay, so that's the end of this lecture on mesh current, and I'm going to go ahead and hit stop recording. Once I close this session, the software is actually going to convert this into an MP4, and it should be available in about 2 hours to actually watch for later. So let's see you all in class.